Thank you very much. Not being myself a string theorist, I'm very honored being invited here, and I thank you very much, all of you, for being here and listening. I will talk about loop quantum gravity, and I will assume that most of the audience here knows very little about this research program. So what I'm going to do is to give you an overview with the main ideas, the main results, and just a few words about the main current lines of investigation. What I'm going to do is to start by discussing exactly what is a problem that is addressed, and an introduction to motivate, to explain what are the loops using here and why, which I will use also to introduce some technical notions like the spin network basis that happens later. And then the main part of the talk, I'll describe the theory. First the kinematics and then the dynamics. Think as if I was introducing QED by first giving the Fock space of the electron and photons creation and annihilation operators, and then the QED vertex for the dynamics. And then I will list some of the main applications. And in particular, I hope I will have some time at the end to talk about the recent calculations of endpoint functions which are used to test the low energy limit of the theory. So what is loop quantum gravity? Is a research program that has been developing now for about more than 20 years. There are roughly 200 people, and there are many books allow me to advertise my own book. What is the problem which is addressed here? The problem is how to describe the elementary degrees of freedom of a quantum field theory when there is no background space-time. The way this problem is addressed is starting from a few hypotheses. So let me put this up front. First, that a radical conceptual change in the way we treat space and time are needed. But on the other hand, that this problem can be addressed within the context of current physical theories, current effective physical theory, generativity plus standard model of some small extension of the standard model. And the reason is that because this problem already is there when you try to define at high energy a quantum field theory of any theory which includes generativity, as I'll discuss. Now, of course, this goes together with another hypothesis, which is an old idea, that the bad divergences of perturbative generativity are not like the ones of the old Fermi theory of weak interaction, a sign of sickness of the theory by itself, but rather an indication that the perturbative theory is not correct in this context. The perturbation around a smooth solution, it's wrong because it introduces, it's a wrong vacuum, it introduces in the theory some extra degrees of freedom which are not there at high energy. And this, I will show, a posteriori is confirmed within the loop approach, where one sees that, in some sense, trans-Planckian degrees of freedom are not there in the non-perturbative theory. Now, the guiding principle, like in so much of modern physics, is symmetry, and is the symmetry under the diffeomorphism group, the action of the diffeomorphism group on the active action of the diffeomorphism group on the fields of the theory, which I'll discuss in the next transparency. Now, consistency with quantum mechanics and generativity and having a fully diffeomorphic invariant theory, explicitly diffeomorphic invariant theory, gives very strong constraints on the theory. The difficulty here is find one theory that has this property, not find which theory that has this property. So for the moment, the problem is finding one. The main result, which I hope to illustrate, is the definition of a theory, or more precisely a framework for defining theories, both in the canonical and in the covariant form, a quantum field theory that has the property of being invariant under diffeomorphism. Now, before beginning, let me make a comment about generativity, because this is a source of misunderstanding often in the communication between different communities. In a sense, general relativity is two different theories. First, it is a specific theory for one field with this action, and which is, of course, well supported empirically at low energy, but we don't know if high energy is corrected and how. So there's nothing wholly about this particular action of generativity from this point of view. However, generativity is also something else. It's a modification of the way we understand space and time. Of course, the idea, or the discovery of Einstein is that space-time is the same thing as the gravitational field. I like to say there is no space-time, there is only the gravitational field. So in a sense, we have moved with generativity from a picture of the world in which the fields live on a given fixed metric manifold to another picture in which the fields live on top of one another. And the problem of doing quantum gravity is, I think, the problem of understanding how to do that in the context of quantum field theory. A solution to how to do that in the problem of classical field theory is, in fact, the one provided by Einstein in 1915. Now, in the theory, this modification is expressed by the invariant and the theory under the action of the diffeomorphism group. The field is defined on a manifold, but then the theory is invariant and arbitrary smooth displacement of this field. So in a sense, the manifold, the physical interpretation of the manifold is washed away by the invariance of the theory. Now, let me remind you, I think that most of you are more or less familiar with old ideas about non-perturbative quantum gravity. In the canonical framework a la Willard DeWitt, or the covariant framework, sort of mostly associated to the name of Hawking, here you have a function of a geometry, invariant and diffeomorphism, a Willard DeWitt equation. Here you have an integral over all four geometries with or without an I. Now, these are beautiful ideas that have inspired much work, but they have never worked by themselves for defining a theory where one can compute things. If you try to compute there, you don't get anything, or if you expand around some background, you get back all the ultraviolet divergences. So in a sense, you can view loop quantum gravity as a way of doing all that to a level of precision where you can start computing and getting numbers out of these expressions. Now, why loops? Loops are an old idea in physics, of course, and there's a long list of major people, some of whom are here, who have argued for the idea of expressing gauge theories in terms of loops. In a sense, it can be traced back to Faraday, right? Faraday introduced field theory as a congruence of lines in space, and then the electric field is just a tangent of the line, of the Faraday line in one point. Now, if there are no charges, the lines may close. These are the loops. And the gravitational generativity also can be expressed in terms of a gauge-like connection and electric field. So there are gravitational closed Faraday lines, and these are the loops we're talking about. Now, question, can we describe a quantum field theory in terms of these loops? Well, the answer is yes, to some extent. And let me again take you back to the physics of the 70s. Take a Young-Mills theory on the lattice in the canonical picture. So a three-dimensional lattice. This is, as far as you keep the lattice space finite, it's perfectly well-defined quantum field theory. There is states and Hilbert space. Operators, dynamics, and so on. Now, in this context, you can define a state by taking the product of the group variables, which are the main variables of the theory, along a loop in the lattice. And this state here is a well-defined finite norm state in the Hilbert space of the theory. It has a property of being an eigenstate of the electric field. This is simple. Where the eigenvalue is zero everywhere, it has support on the loop itself. So it's literally a quantum excitation, a single quantum excitation of a Faraday line. Now, these loop states by themselves do not form a basis in this Hilbert space, but a simple generalization of the same object does. And these are the so-called spin networks. You take a spin network is a graph on the lattice here, colored with some representations on the graph links and representation of the gauge group and some intertwiners some invariant tensor in the associated with the nodes. Now, for each one of these objects, you can construct a state, basically by contracting the invariant tensor with the representation elements. And these states, again, have the same properties. So the eigenstate of the electric field where the eigenvalue is concentrated on the graph, and their basis, or orthonormal basis in the Hilbert space. So, as far as you're on the lattice, you can transform everything to this basis and represent entirely Yang-Mills theory in terms of this Faraday lines and operator acting on them. Now, can you do the same on the continuum? The answer is no, essentially because these are too singular. If you move infinitesimally one of these loops in the continuum, you get, you assume this is an orthogonal basis, you get an orthogonal state, and if you take this as a definition of a Hilbert space, you define something much larger than this Hilbert space that you want. However, and this comes the good point. So far I've given you difficulties in a sense. The old quantum gravity, perturbative quantum gravity does not work. The idea of describing quantum Yang-Mills fields in the continuum in terms of loops or spin network does not work. Now if you do the same together, each one cures the difficulties of the other one. And a loop formulation of gravity or a Yang-Mills theory coupled to gravity works in the sense that I will say in a moment. It solves both sets of difficulties. And why? Because of diffeomorph invariance. Here is where diffeomorph invariance come playing a role. So take one of these spin network states, deform it. Now, if the theory is diffeomorph invariant, these are gauge equivalent description of the same thing. These two states are related one to another by diffeomorphism, like two metrics obtained by smoothly deforming one to another represent the same physics. So the gauge invariant states, the equivalence classes of this object under smooth deformation are abstract graphs labeled only by the graph, its knotting, and the quantum numbers. So in a sense, the smearing over the manifold is done automatically to you by gauge invariance, which takes away an enormous number of apparent degrees of freedom in the position of these things. Now, so far was just sort of motivation. Let me become more precise here. Now I start saying sort of more precise things. So how is this series defined? We'll start with generativity or generativity plus a standard model. Or basically any other diffeomorph invariant theory in which the basic variable is a connection. In generativity we use the Ashoka formulation. You do a canonical quantization. Go to a basis of spin network states of the one that I just introduced, impose diffeomorph invariant, study the Wheeler-DeWitt equation. These constructions give a separable Hilbert space of state, an algebra of operators. In the Hilbert space of gauge invariant state, there is a basis which is given by these abstract graphs labeled by spins and intertwiners, and the dynamics turn out to be ultraviolet finite. Now, let me give you some more details. How is the Hilbert space defined? One starts by a Hilbert space of non-gauge invariant states, which is constructed in terms of functionals of the connection, cylindrical functions that just depend on a finite number of holonomies of the connection. And on these, there is a scalar product that can be defined, which is SU2 and diffeomorph invariant. So this Hilbert space carries a representation of diff, and if you take the quotient by the gauge group, you get a well-defined, you can show that you get a well-defined Hilbert space. The operators which are well-defined there are the holonomy itself and the operator conjugate to it, which is the electric field, the object conjugate to the connection, which is a two-form, integrated on a surface. And this acts as a left invariant vector field on the group element associated to all the lines that cut the surface. Now, this representation, this is a theorem. First of all, this Hilbert space is a representation of the Poisson algebra of those operators, of those classical operators, and is unique. This is a theorem, it's called the Lost Theorem for the name of the people who have proved it, which in a sense solidifies this construction. The theory was constructed by hand, sort of physicist style. The representation is unique up to unitary equivalence, namely, basically, if you want to quantize the diffeomorph invariant theory in terms of these observables, this is the only thing you can do. Now, what is in this Hilbert space and these operators? First result, take a region of space and consider the volume of this region of space. Now the volume of course depends on the metric, which is a gravitational field, which is one of the fields we have, so it's going to be one of the operators in this Hilbert space. And it turns out that it's a well-defined self-adjoint operator. One can study spectral problem. The spectrum is discrete, and the eigenstates are the spin networks. And what is interesting is that the eigenvalue of the volume get contribution from each of the nodes which are inside the region. So you can think at each node as a contribution to the volume, so a quantum of volume. The same game can be played with the area. Again, the spectrum can be computed. This is the spectrum. And the area now gets a contribution for each link that crosses the surface. So you can think at each link carrying a quantum of area. So this leads to a description of quantum space-time, which I find beautiful, compelling. So these abstract graphs can be interpreted as a quantization of space, quantum excitation of space, where each node is a quantum of space. The graph gives the connectivity, who is next to who. The intertwinedness of the quantum number of the volume, and the spins are the quantum numbers of the area. So these are not excitation in space. Notice that there's no position, momentum, energy, nothing like that here. These are excitation of space, okay? These don't live somewhere. These are the spaces. So this is the way in which the theory construct a diffeomorphic invariant, a background-independent quantum description of space. And the discretization of space here comes here not from the graph, but from the discreteness of the eigenvalues of volume and area. So this is a cartoon comparison with strings. If you think a string, in both cases, both theories explore the idea that extended one-dimensional, high-dimensional excitations define the interesting quantum field theory, but in strings you consider these things on a space-time, at least in the basic definition of the theory. In the loop approach, you consider these things are building space-time themselves. Now, what about the dynamics? Now, first way for defining the dynamics to write the Wheeler-DeWitt equation. So this is obtained by writing this operator, starting from the Hamiltonian constraint of the classical theory. So this is a construction. I'm not giving you the construction, I'm giving you the result. H is a well-defined operator, and it is ultraviolet finite on the diffeomorphic invariant state. Let me give you a sketch of why this happened. To define it, there's a curvature which is regulated by sort of point splitting in terms of an holonomy, and then you have to shrink the loop to 0. Now, what happens when you shrink the loop? See, this state here and this state here are the same in the diffeomorphic invariant theory. So what's happening is that the limit alpha to this is just a sketch of the mathematics, but what happens is that the limit is trivial on the diffeomorphic invariant state because concretely there is no short distance in the theory. Everything exists in a sense only on the Planck scale. So the theory is ultraviolet finite. This can be done with matter also. Nothing really changed substantially with matter. The gravitational field is not special here. It's the existence of the diffeomorphic invariants that makes the theory special. So what is special is the theory when the gravitational field is not a fixed background, but is a dynamical object. So if you have a Yang-Mills field, what happens is simply you have the same abstract graphs with extra quantum numbers, which represent sort of the Faraday lines of the Yang-Mills field. Now there is a covariant description of the dynamics, which works much better to compute things, which can be obtained by studying the projector on the kernel of the Wheeler-DeWitt constraint and expanding it in an appropriate sense. And a la Feynman, like in Feynman thesis, are organizing the terms in terms of sort of histories of spin network. And the result is that you can write the amplitude as sums over histories of spin network, where the amplitude comes from the action of the Hamiltonian constraint on, turns out, on the on a discrete set of points. These histories are what is called spin forms. A spin form is a two complex, so there are surfaces here that meet on edges that in turn meet on vertices, labeled with spins and intertwiners. And the action here is in the vertices. There is an expression for the vertex amplitude, which is I've given here. This is the Wigner 15J symbol. These are some Puser coefficients, some sort of natural SU2 object that come in. And this action here define the dynamics of the theory in the sense in which the QED vertex defines the dynamics of QED. Now this formalism here, this covariant formalism, I just summarized here. This is full definition of the theory in the covariant. So you have a partition function which is a sum over spin forms. So these two complexes labeled by spin and intertwiners. There is some measure factor and the product of over the vertices of the amplitude. The amplitude is written here is a function of the J and the I. This covariant representation of the theory can be looked at from a number of different points of view. It can be, first of all, you can forget everything I've said coming from the canonical, and you can directly derive it by discretizing the action of generativity on a lattice. You fix a lattice, a triangulation, you discretize the theory, you go to the dual cellular complex dual to the triangulation. This is what gives the two complex, and you sort of Fourier transform, and you get this expression here with this amplitude here. What you don't get from this point of view is the fact that if you do that you work on a fixed two complex, while the expression you get coming from the covariant point of view is a sum over all possible two complex. This is what implements fully the background independence of the theory. This can be also interpreted as a sort of well-defined version of the Hawking integral. Each one of these objects can be interpreted as a geometry. And most interesting, exactly this expression can be obtained as the Feynman expansion of an auxiliary field theory, exactly in the same way in which matrix models generate two-dimensional quantum gravity. Now, there is a generalization from 3 dimensions done by Bulatov to 4 dimensions done by Uguri of the matrix model, which gives an expression very similar to that, which can be read as a quantization of BF theory. If you add to BF theory some constraints, the constraints that transform it into generativity in the classical theory, and if you impose this constraint in the quantum theory, you transform Uguri theory exactly in this expression here. So, in a sense, this is Uguri's BF quantization plus the constraints that transform BF in generativity. There you have a single SU2 15J symbol. Here you have 2 because there is SO4 behind in a sense. Now, I have very little time. Let me fly through some physical applications. I just want to mention 3, I guess. First, loop cosmology is one of the main line of development today. What is interesting is that unlikely the Wheeler-DeWitt mini superspace quantization that is still singular at t equals 0, if you start from the loop theory and you do a mini superspace quantization, what you find is that this singularity is removed in a sense because there is no because the theory is non-local at a very short scale, and in fact the Wheeler-DeWitt equation can be continued to the other side of the singularity. So you have a bounce, and this bounce is robust. Is there both if you do closed universe, open universe with cosmological constant, without cosmological constants, and there's much activity going on in this direction. There is indication of an inflationary behavior at the beginning, the calculation of the spectral index, scale invariance. I'm not going into the detail. A classical result in the theory a few years ago is in regards to black hole. The entropy can be computed, is finite, is proportional to the area. The calculation can be done for physical black hole, Schwarzschild, Kerr, and the coefficients 1 over the 4th is obtained only adjusting a free parameter that floats around in the theory, which I'm happy to answer any question if you have about it. What is most interesting in the black hole physics, I think, is what happened at R equals 0. There's a number of recent results indicating that also the R equals 0 singularity is resolved exactly the way the cosmological singularity is resolved. There is a region in which space-time is not defined, is quantum, and then the space-time can be continued so to the other side. Now, in the last minutes, I want to tell you about these endpoint functions and low energy limit of the theory. Let me start from this. It's notoriously difficult to define endpoint functions in the case of different invariant theories. Essentially, x and y here are coordinates. So if the theory is invariant under coordinate transformation, it doesn't mean anything. One way to go around it is, you see, one has to find a way to find to fix a distance between x and y, the geometry here. Bring the geometry inside. So one way is to break this integral in the integral inside, on the boundary, and outside a given region in space-time, so a four-dimensional finite region of space-time, and then replace the outside integration with a state and view this as depending on this state and choose this state as giving a geometry to the boundary. So in this way, one defines another object, which is an object which depends on x and y and the geometry on the boundary, which is the right object in the different invariant theory that can be compared with a boundary, with a two-point function, in this case, of the background dependent theory. So what's going on physically here? Imagine that here, let's see, you have a scattering experiment. There's an interaction region, so it's a closed space-time region. You measure the fields corresponding to the particle going in and out, and you measure distances and time lapses around this region. Now, this is a field measurement. This is also a field measurement if you bring generativity in, because these are just measure of the text of gravitational field. So the only thing you want is the amplitude of the process at given values, boundary values of the fields. Now, you can use this logic within the theory, find a way to fix the boundary states, fix the geometry in terms of the boundary state, and use this to compute, for instance, the graviton-graviton two-point function, which is a certain well-defined expression here. And thank you. It turns out that in the limit, in the large distance limit, so when the boundary geometry is large compared to the Planck length, this is dominated just by the vertex, or more precisely by the asymptotic expansion of the vertex for large j. So this is being computed. There's a lot of activity trying to make this precise, and this has been computed in some variants of the theory. There are preliminary results which give the free graviton propagator a three-point function, and hence Newton law, and some first-order corrections to the free graviton propagator. Now, again, here there's a lot going on. I don't go into any detail. So let me summarize. First of all, loop quantum gravity is a technique for defining different invariant quantum field theory. It offers a new description of space and time by merging quantum field theory with the different invariant introduced by generativity. Now, the theory defined here is substantially different than most of the quantum field theory in which we know how to work. Notice there's no energy here, there's no momentum, there's no natural definition of S matrix, nothing like that. The theory lives only on the quantum state, on its own quantum states. There is a definition of a quantum theory of generativity plus a standard model in 4 dimensions. It's naturally ultraviolet finite, and it has, in the sense I've said, a discrete structure at the Planck scale. The application in cosmology, black hole physics, which I mentioned, astrophysics, which I did not mention, and a way of addressing the problem of the black hole singularities and the cosmological singularities. Now, minuses and pluses, in my opinion. First of all, if this is correct, well, of course we don't know, there is nothing here related to the unification of the forces, right? So the problem is not addressed at all. So if this is correct, this is not in any sense near the end of physics. As I've hinted, that there are different definitions of the dynamics. The definition of the canonical and the covariant theory are not being proved the same. Within each of the two, there are variants which are being considered. And these low energy calculations which I mentioned, which I think are crucial to compare the theory with generativity and therefore test its validity, are still very much in progress. what are the pluses? First of all, it's a formulation of quantum gravity where the fundamental degrees of freedom are explicit. The theory is fully consistent with today's physics, simply so, because there is no special constraint on which fields you have to put in the difference invariant theory. And so in particular, there is no need for high dimension and there is no need for supersymmetry. There is some literature of the formulation of supersymmetric theories in this language and even high dimensional theories in this language, but there's nothing that requires them, which of course you can view as a plus or a minus, in my opinion, until we actually see nature or LHC tell us differently. I still see this as a plus. And finally, the theory is consistent and is based on quantum mechanics and general relativity key insights, which I think with the standard model are still the main source of reliable information we have about nature today. Thank you.
Some questions? So Simon.
I had one question with two parts. So,
okay.
Yeah, the first is, so you talked about getting the entropy of Schwarzschild black holes, but if the low energy limit is still in progress and you don't have a low energy description of flat space, what does a black hole mean? Then the second half is, there's a freely adjustable parameter which can change the Bekenstein-Hawking entropy. So in contrast to a narrower approach, like string theory, which is only capable of getting the correct classical limit for Bekenstein-Hawking entropy, is that an issue?
Let me answer to the second question. Yes, it is an issue. We would like very much to have an independent way of fixing this parameter, of course, and so far it doesn't exist. You can compute the entropy for different black holes, Kerr, Schwarzschild. There's a number of calculations with some matter, without some matter. There are a number of consistency conditions. One is that this value of this parameter is the same in all cases, so this works well. What would be useful, what would be conclusive, is to have an independent low energy calculation where this value is understanding what fixes this value of this parameter in the theory by itself. So yes, it is an issue. The other question is, given that you said, given that you don't have a low energy limit, how do you know that you're doing a Schwarzschild black hole? That was
in progress. I don't know how far it's progressed.
Yeah, no, but sure. I take. There are different ways of defining an event horizon in general relativity. You can define it non-locally in terms of what happens at infinity, so to the boundary of the past or future infinity, or you can define it locally in terms of the local property of the gravitational field in classical general relativity. There have been much advances recently in giving this definition. So the theories construct in terms of this local definition of horizon. So if you have in classical general relativity a metric that has this property, you look what happened there and you continue this.
I see there are a lot of questions, so let me just moderate. Is there any other question related to this question in sequel? Okay, if it's not, Steve?
In scientific models of 2D quantum gravity, one is often afflicted by a branched polymer phase above one dimension. Can you show or can you discuss whether that is a problem in these spin foam models?
No, I don't. I don't see the analogy. When you go from 2-dimension to 4-dimension, everything changes entirely. You don't have the double scaling limit. The theory is substantially different. So I don't know how to read in the 4-dimensional theory those kind of at all.
Okay, so
it doesn't mean that they are not there. It means that we do not understand the theory at the point of understanding that.
Okay. Next one.
I think this was almost a little puzzle. To reconcile perhaps the way we quantize gravity in string theory, if you like, and what you try to do, seems to me that you are in the topological phase. because in a sense, to have full diffeomorphism invariance is a bit too strong. In the usual case, diff is broken down to local Lorentz, and that's, in a sense, generates the graviton as a Goldstone mode. So it seems to me that we are on the side where you have somehow some form of breaking of diff invariance, and you are on the side which is purely topological. The difficulty is that I do not know how to go from one to the other.
Yes, thank you for this question. I would make a distinction a little bit more fine. There are theories which explicitly, let me talk about the classical theory first, otherwise. There are theories where there is no action of diffeomorphism group whatsoever, so Maxwell and Young-Mills. There are topological theories, right, like BF theory, which have the property that there are no local degrees of freedom. You only have global degrees of freedom. And then there are theories like general relativity, which have local degrees of freedom in some appropriate sense. I mean, there are gravitational waves and so on, but nevertheless, which are diffeomorphism invariant. The theory is diffeomorphism invariant, and such that in the classical theory, all the observables, all the things that you measure, have an interpretation as diffeomorphism invariant observables. Now, let me answer a little bit more precisely. This is the sort of the covariant definition of the theory. As I said, this resembles a lot to the Auguri quantization of BF theory. Now, in that theory, there is no sum over the two complex. And in fact, one proves, formally and precisely if one goes to the quantum group and makes everything finite, one proves that the expression turns out to be independent from the background triangulation, which means that whatever you compute is dependent on how much you refine the triangulation inside, and it's a topological theory. So that BF is a topological theory. In three-dimensional case, this is very nicely. Here, there's nothing like that. This expression here is not independent from the. Once you impose the constraints, basically you write B as E wedge E. You break this topological invariant. You bring degrees of freedom there. This does not mean at all that the theory is topological. There are all the degrees of freedom. This is the quantum equivalent to the classical fact that general relativity has the full diffeomorphism invariance, and at the same time, what I'm saying is that between your two pictures, there is only one in between.
Yeah, there's been a revival of interest in our field in three-dimensional gravity. For example, Witten's work of a year ago. There was a very interesting talk here by Andy Strominger. Has anyone in your field tried to make contact with that work? So there's the conjecture is that three-dimensional, for example, negative cosmological constant gravity would have a two-dimensional dual, which would be a conformal field theory with very specific properties. And what's surprising about it is that a conformal field theory has a much larger degeneracy of states than you might have expected from gravity, and these are supposed to describe black holes and perhaps other excitations. So it seems to be there is this conjecture that it's a much more solvable system, and I'd understood that three dimensions was a much more tractable case in your formalism as well.
Yes, it's great you asked this question because there are loop conferences, and we invite string theories regularly. The last one was Maloney, who was here, I guess, and he gave a talk about three-dimensional quantization. It was very nice. And in fact, at the end, everybody raised their hand and asked this question. Namely, oh, this is very great, but have you tried to compare this? And the answer is no, apparently, which I think is very bad. I mean, there's a lot of literature in three-dimensional quantization of 3D gravity, both in the Euclidean and in the Lorentzian, with the zeta, without the zeta, in a number of things. There are books. There's Catholic book. There are beautiful things like the 2L0 state sum model, right, which is a finite sort of topological invariant in the compact case. So that's compact. Cannot talk with the other one. I think somebody should sit down and compare all these things, and it should be done, definitely.
Okay, next question, go ahead.
You have mentioned that in this scheme, the Hopkins formula is reproduced with a certain value for the immersive Barbero parameter, which is fixed. I mean, it is found, really. But this value is completely different from the earlier one in the approach of Asketar. Is there not a contradiction, or how does it go? Because this gamma is a value which is fixed by comparing with the classical result. But then this gamma is a value, I don't remember how much is it, but I remember that it is different from the original one in the Asketer approach.
Yeah, so, maybe for those, so...
In fact, it was complex even.
The action of GR in this formula is this one. This is the tetrad, this is the tetrad, this is the curvature of the connection. Now, this extra parameter is this one. So there's no dual here. The dual is on the internal indices. These are, let's do the Euclidean, SO4 indices, or Lorentz indices. This term here is a topological term in the sense that it does not affect the equation of motion. If you fix the connection to be the one determined by the triad, this is the pseudoscalar curvature, which is 0. Right. So, but if you have the E and the connection independent, this is not necessarily 0. So this is 0 only a solution of the equation of motion. So the issue is this gamma here. Now, when Asketer wrote his formalism, he basically did a canonical transformation which consists in adding this term here, and chose the value gamma equal I. Okay? Knowing very well from the point of view of the formalism that this is one possible value. This is one possible value that in fact has the advantage of simplifying part of the theory. If you take a real value, you don't get this simplification. The classical theory is always the same. It doesn't change. In fact, it's simpler from another point of view. So one issue is which one is the correct value in the classical theory, and there isn't any correct value in classical theory. You have a one-parameter family of formalisms that give the same equation of motion. One issue is what is the correct value in the quantum theory. This is like theta QCD, if you want. It's very similar, in fact, to theta QCD. Now, the only indication so far we have about the correct value in the quantum theory, if we believe all this, is that in the black hole entropy formula comes out with one particular value of gamma and not any arbitrary one. But this is not in contradiction with early choice.
How much is it? 3 point something?
Square root of something. Log.
Any other question? Okay.
Thank you. You mentioned quantum cosmology as application of loop quantum gravity. But can you derive quantum cosmology from loop quantum gravity, from four-dimensional theory? I mean, do you have some prescription of dimensional reduction or of these spherical ansatz which reproduce cosmology?
No, depends on which level of precision you want an answer to this question. I mean, if you want a rigorous derivation of loop quantum cosmology from loop quantum gravity, there is not. If you want a very hand-waving derivation, yes. Basically, loop quantum cosmology, in its simplest realization, is just a quantization of finite-dimensional cosmology, bringing in some input from the quantum theory, from the continuous theory along the way.
It's not exactly application. It is rather a model.
No, it's not exactly application. Yes, I would say, yeah. I mean, it's like, string theory and theories that are related to string theory. Is that, let me answer precisely. There is no way to start from this Hilbert space and algebra operator that I gave in the continuous theory and derive the canonical formalism. There's a lot of work in that direction.
Okay, I think we are closely over time. So I propose to postpone all the discussions during the break. Okay, let's thank the speaker again.